Alright, Spinners and Twisters episode 3. We are now going to talk about how particles can be described by Lie and Clifford algebras. And we aim to do this in a very geometric way because I want to provide you an understanding of Lie algebras in a way that most other YouTube channels don't do. Most YouTube channels will provide you with a very abstract definition, and we want to make things as geometrically intuitive as possible. So let's go ahead and dive right in. Again, I want you guys to keep these two animations in mind as we proceed, not just in this video, but others to come, because what I aim to do again in this series is to come at things from a fundamentally geometric perspective. With your titanium subscription on Patreon, you'll be able to have access to the source code for the animations in these videos. And this video is sort of going to be video 1 in quite a bit of series diving deep into Lie algebras because we really need to understand those to continue with understanding twisters. Alright, so there's a few things that I would like to address first from the last video that I seem to have overlooked. In the very last slide, I accidentally misspelled Roger Penrose's name. This was my bad. In making these videos, there are just some things that I check a million times and I still seem to overlook. Also, it has come to my attention that all of these spinners were named after the last names of these people that proposed these spinner objects. And so I'll call these Penrose spinners for the sake of consistency. Anyways, with that out of the way, let's continue. I want to ask you a question first. What is this shape minus this shape? Well, in this video, we are going to address this with Grassmann, Clifford, and Lie algebras. What I will do is turn this into a very geometric question, and then we're going to do this with some animations to make it very clear. The two shapes are periodic, but they don't necessarily have to be. One could be very aperiodic, if you wish, and the other could be just a static point. If you watch this until the very end, you will see how this not just applies to 2 dimensions, but in as many dimensions as we want. So let's go ahead and address this issue, or this question. We aim in the next few set of episodes also to understand the following matrix generators for the conformal algebra. We will go over what exactly a conformal algebra is, but roughly speaking, it's a more generalized Lorentz algebra. Put another way, conformal transformations are Lorentz transformations with 2 additional types of transformations. I know I'm saying transformations a lot, but this algebra comes about by introducing transformations that render the metric scaled. We are going to see how Lorentz transformations naturally generalize to Poincare transformations, and then we will add 2 additional transformations, namely dilations and special conformal transformations, which are transformations that just scale to the metric, or to scale the metric. After this, we will get the generators both in operator form and in matrix form, which is what you are seeing here on the screen right now. These are the matrix form generators. And these are the rotations in the special orthogonal group SO42. And these are the boost matrices. This is a set of a total of 15 generators. They will not only be relevant in twister theory, but also in string theory. Conformal transformations are also important in understanding many other interesting natural phenomena, such as phase transitions. Alright, so as per usual, I want to pay some respects to Hermann Grassmann. I think you pronounce his middle name Gunther, but correct me if I'm wrong. The one thing I'll say about Hermann Gunther Grassmann is that he embarked on a quest in the 1830s to attempt to unify all of mathematics. Right? And he came up with this idea of the Grassmann algebra, or the exterior algebra. And that's what we're going to talk about in the first part of this video. The core of his theory emphasized an algebra of space, which allowed for the manipulation of geometric objects in geometric space. He offered to the world a formalism in which we could add and subtract shapes from one another, essentially, which is why this is often referred to as geometric algebra. And we're going to get more into that later and how it connects to Clifford algebra as well. Anyways, let's dive straight into Grassmann algebra. Okay, I want to get at Grassmann, Clifford, and Lie algebras in a very geometric and dynamic way. We could start by considering two vectors and taking a determinant between them. This turns out to be the area of the rectangle whose two opposite points touch the tips of each arrow. We can see this in this animation, that the area completes an enclosed area that contains the other two areas. In this way, we can think of any arbitrary area as being composed of components just like vectors are. And we can do the same for volumes. For volumes, we just add another vector to the determinant and play the animation. In 4 dimensions, we can't really visualize this, but mathematically we can write it down as still a determinant. The pattern is the same. And so we can think of the determinant as being an offset area that can be broken down into smaller areas that are determinants and that touch the center of the coordinate axis. Notice that if we were to put the vectors in opposite order in the determinant, then we just get the negative of the original determinant that we had set up. This is to say that the determinant is antisymmetric upon this swap. This is going to be true for any volume as well. Swap any two vectors in the determinant, and all you have to do is change the sign. The volume itself doesn't change in value. There's just a sign swap which gives it a sense of orientation. We are going to call this operation the wedge product between two vectors. And so, in a very geometric sense, we can think of this thing that we are calling the wedge product between two vectors as being the enclosed area that we see in this animation. I like this understanding of the wedge product the best because it's very geometric and we can see what a function over time will do to this area. A function can be thought of as doing the rotation that we are seeing before our eyes, or it can only apply to one of the vectors and expand it, thus enlarging the area. Or it could do both while also changing the rates by which these arrows rotate. The point is that these areas or the wedge product can be very dynamic, and this is going to be useful for something later that we'll call p-forms, and this is more of a topic for tensor calculus, but that's another playlist. Anyways, so the wedge product can be thought of as a generalized determinant in multiple dimensions, and geometrically the determinant can be thought of as the sort of offset area or volume from the origin. The area is antisymmetric, giving a sense of orientation to it, and it is linear in all of its properties. All of this can be categorized as the Grassmann algebra. This also forms the basis of what are called p-forms in tensor calculus, which we won't go into too much detail here, but if we look at a 3-form, for example, this is an antisymmetric tensor that has a very similar structure to an enclosed volume. This is more a topic for tensor calculus, like I've said, but this is to say that the coefficients here, the omega values, can be a function of time, giving us back this idea of dynamic volumes. So going back to my original question on what the difference is between these two shapes, well, we can now understand these shapes as being traced out by these vectors and the enclosed area that is made between each vector can be plotted. As the vectors move in time, the area is a function of time. Animating this notion is relatively easy. All we have to do is create an updating function that just plots the area over time, and there we have it. What is interesting is that this function looks repetitive, but it isn't because of how each vector is moving. If we look closely at the function, the peaks don't exactly match in different regions, but if we run this for a very long time, then we can start to see a pattern emerge. So this is a really good way at creating locally aperiodic functions but globally periodic ones, which is, in my opinion, very interesting. Anyways, let's now connect this with Clifford algebras. Now we want to cover the concept of Clifford algebras. But before I do this, again, I want to pay my respects to Clifford himself. So his name was William Kingdon Clifford, and he unfortunately died at a very young age due to tuberculosis. but he made major contributions to the world of mathematics and the study of quaternions. In 1876, he wrote a work called On Space Theory and Matter, in which he presented the idea of matter and energy being one and the same thing, and this was very much prior to Einstein proposing the same thing, when Einstein started coming up with the ideas of special and general relativity. So in some sense, Clifford was the OG Einstein, right? He was theorizing about this stuff before Einstein was even born. In this sense, Einstein's theories might not have been as novel as they were. Anyways, let's go now into Clifford algebras. We can consider the quaternions. Quaternions are considered four-dimensional numbers. We also have octonions, but we're not going to talk about those right now. One of the components of the quaternions is completely real, whereas the others are not. They are in front of three symbols that all square to -1. And we want to be as abstract as possible here, and we'll get back to the geometry, but this is key for our understanding of Clifford algebras, and many other algebras that we'll talk about later. We say that the quaternions contain three basis elements that square to -1, and so we say that the Clifford algebra for the quaternions is CL03, with 0 meaning that there's 0 symbols that square to +1, and 3 meaning that there's 3 symbols that square to -1. It's important to note that the number I is not the only thing that squares to -1. We can have matrices that do this also. And more generally, we can invent any number of symbols that square to -1. And this is going to be important when we start talking about split algebras also. Importantly, however, the Pauli sigma matrices are things that square to +1. For the Dirac matrices, one of them will square to +1, and the rest will square to -1. We can find such four matrices that obey anti-symmetry rules also, and this is important. And when we do this, we see that we have two different bases for Dirac matrices. And again, these matrices are part of the Dirac equation, which act on Dirac spinors, which are a coupling of left chiral-Weyl spinors and right chiral-Weyl spinors, which come from the special linear matrices that cannot be charge conjugated. This is, again, I'm going all the way back to concepts from previous videos because we want to keep old concepts at the forefront of our mind. And so for our Dirac matrices, we have that the Clifford algebra is CL13, with one symbol gamma 0 that squares to +1 and three symbols that square to -1. This is very reminiscent of space-time. Also, typically when we multiply vectors together, we say that the multiplication between two basis vectors that aren't the same is 0 because they are orthogonal to each other. However, if we were to say that the multiplication of basis vectors obeys the Grassmann algebra, then we allow for the multiplication of two vectors to be the sum of their inner product and their wedge product. This is geometrically quite fascinating because this product can be thought now of as the sum between two functions if we were to look at the following animation again. So the two functions that we see at the very bottom, we can actually quite literally understand the multiplication of two vectors now over time as being the sum of these two functions. Anyways, let's continue. Connecting things with what we saw in Grassmann algebras, we can see that these sigma matrices have antisymmetric properties similar to how we saw the wedge product. So embedded within these Clifford algebras are Grassmann algebras. On the left, we can think of these as Pauli vectors, Pauli bivectors, and Pauli trivectors. Trivectors are weird because there is only one basis vector that we're seeing right here. And so these are typically thought of as pseudo-scalars. For Dirac gamma matrices, we have Dirac vectors, Dirac bivectors, Dirac trivectors, and a Dirac, if you want to call this a quad vector. Again, there are mappings between these spaces because they match in dimension. However, for the Dirac bivectors, there's no such mapping. Rather, such Dirac bivectors contain an automorphism, which is a map between itself. And we're not really going to talk about this right now. All right, the big boy himself, Marius Sophus Lie, or Lie. Again, I've heard it pronounced different ways. pronounce it what you will. This channel is mostly dedicated to physics and math, but again, I want to pay my dues or pay my respects to Sophus Lee. He was a giant, and he currently still is a giant in the world of theoretical physics and mathematics, primarily because when we describe particles, we are describing them in terms of Lie algebras, right? And Lie algebras are, so in this sense, Lie algebras are very, very important. So he did a lot of his work in Norway at the University of Oslo. The core of his work lies in the notion of continuous transformation groups, and this revolutionized the theory of symmetry in geometric structures. This is going to be hugely relevant in talking about modern physics, modern particle physics, abstract mathematics, because this is at the core of almost everything. And so as we progress throughout this series, we're going to see how Lie algebras really do fundamentally help us understand particles and the nature of particles. Unfortunately, he passed away at the young age of 52, but his legacy is going to remain for a very, very long time. So with that being said, let's go ahead and get started on Lie algebras. Okay, Lie algebras. I'm going to cut straight to the chase here. The basis of Lie algebras comes from our ability to exponentiate matrices. Let's see how this works. First, we can take the exponential of matrices themselves, and we can find that there's a pattern. Given this pattern, we can realize that if we were to exponentiate such a matrix, and then use the Taylor series, we can see that this becomes a standard rotation matrix. We just use a parameter theta to make this happen. So looking at this really quick, what this essentially enables us to do is turn a single parameter theta in an exponent to an angle of rotation in vector space. So exponentiating this matrix along with a parameter theta will give us the same rotation in 3D space, and we can see that the relationship between these two matrices is given by the following equation. We can confirm this through an example. We take a rotation matrix, take its derivative, and then set the driving parameter equal to 0, and we get something that we'll call a generator matrix. Okay, so we have a number that we place in an exponential along with the matrix. By using a matrix in the exponential, we have generated a rotation. Contrast this for a second to what happens when we take the exponential of a complex number. Taking the exponential of a complex number changes an exponential function into a sinusoidal function, and this is seen in the famous Euler identity. Whereas taking the exponential of a matrix turns a simple exponential function into a vector transformation, i.e. a matrix. With all of this in mind, we can imagine that these matrices live as points positioned on a sphere where the angle tells us how far from a point we are on that sphere. Tangent vectors are nice linear objects, and they obey all the rules that regular vectors do, which are that the sum of two tangent vectors is another tangent vector, the scalar multiple of a tangent vector is another tangent vector, but also that the commutator between two tangent vectors is also a tangent vector. But in order for this last condition to work, we need things called structure constants. Since derivatives are tangents to their corresponding curves, then we have that the generators are represented by tangent vectors on the sphere, and we can see that in this animation. Recall that these angles represent the angles by which Lorentz transformations occur. So, in essence, this sphere represents all the rotations that occur during Lorentz transformations. This is not to be confused with the Poincare or the Bloch sphere, which again are spheres that represent polarization and spin states of particles. These rotations do not necessarily create closure within the group, so we add things called structure constants in order for this to work. For SO3, these structure constants take the form of there being 3 by 3 antisymmetric matrices. This makes it so that the commutation between two generator matrices behave like tangent vectors on a manifold like a sphere. So in a very real sense, these structure constants give our continuous transformations a geometric structure. and behave much like tangent vectors would. If we were to do the same for Lorentz transformations, these are transformations that involve the time component now, we get standard rotation matrices in space that are generated by these matrices and boosts in spacetime, which are generated by these matrices. And putting everything together, we have that for polyvectors, rotations are exponentially generated by the matrices, whereas polyspinor Lorentz transformations are exponentially generated by these spin matrices. These generators are classified under the Lie algebra lowercase SO3. For our spacetime vectors, rotations and boosts are exponentially generated by these matrices, and for Weyl spinors, their transformations are exponentially generated by these matrices. Together, these form the Lie algebra of lowercase so plus 1, 3, where the plus means that the spacetime is orthochronous, where the time component is positive and the space components are negative. Because we can flip this or flop the signs if we want to do that. We just need to make it so that the time component and the space components are opposite to each other. The 1 refers to one symbol or matrix that squares to positive 1, and the 3 again refers to the symbols or matrices that square to negative 1. And so we have found that there are two ways of going about identifying particles. There's the Clifford way and the Lie way. Let's review for a second. The Clifford way entailed identifying symbols or objects that squared to positive or negative 1 and then packaging this in an algebra. This is instructive because we found that Dirac matrices obeyed different algebras or a different algebra than the Pauli matrices, therefore telling us that Dirac fermions obey a fundamentally different algebra than the Pauli ones. The Lie way entails that we take the Lorentz transformations of some object, in this case I took a Pauli spinor, and find its generator. For completion, I started with a vector reminding ourselves to place it in the Pauli formalism, and then use the sandwiching that we saw in the first video, linked here, and then found the generator. It is important to recall, again, that the Pauli sigma matrices are not the same as the Lorentz generators. They were the matrices that we found rotated spinors around a Bloch sphere. The Pauli matrices are the generators for spatial rotations of spin 1/2 particles, and they are a component or building block used to construct the full set of Lorentz generators in the spinor representation of the Lorentz group. They are not the same set of 6 generators, but rather a subset, which is the rotation part, or a basis for the representation space of those generators. Okay, we've gone through a lot, so I will leave you with this final thought. We have these Lorentz transformations and these things that generate them, and it is quite obvious to us at this point now that Lorentz transformations are the things that transform space and time together. But what about the spinor representations of these transformations? It is said that these things are also Lorentz transformations, but they operate on things that only have 2 components. So what gives? We say that these 2 components are internal degrees of freedom that are subject to the transformation rules that are given to us by such representations. So instead of transforming space-time, there are internal properties about these particles that change according to these representations. And these internal properties will give the names such as spin and color, as we'll see later. And contained within the algebraic structure that these internal Lorentz transformations describe are areas given to us by their Clifford algebra. Another way of saying this is that our spinors can be described by area components rather than basis vector components. And this is going to be important to keep in mind as we continue with this series. Anyways, make sure to hit that like and subscribe button, and I'll see you guys in the next episode. Bye.